You know those massive AI models that are basically powering everything now? Well, training them is one of the biggest, most expensive challenges in technology today. But what if we could finally tame a key part of that process? A part that, until now, has been a totally chaotic guessing game. Today, we're diving into a breakthrough that does just that, turning the art of AI training into a predictable science. Just to give you a sense of the scale we're talking about here, the reinforcement learning phase, and that's just one part of the training, can eat up over 100,000 hours on super specialized computer chips called GPUs. That's an absolutely astronomical amount of time, money, and energy. And get this, the price tag is only getting bigger with every new AI model that comes out. So here's the thing. The first part of training in AI, the pre-training, follows some pretty predictable rules. But the next, super critical step, reinforcement learning, or RL for short, that has been a complete Wild West. Researchers literally had no reliable way to know if their ideas would actually work at a large scale, which made the whole process feel like taking a series of very, very expensive shots in the dark. So imagine this. What if you could know, right from the beginning, whether your multi-million-dollar AI training project was headed for success or if it was doomed to fail? That is the exact question researchers set out to answer, and what they found could honestly change how we build artificial intelligence forever. All right, let's really get into it, because to understand why this is such a huge deal, you first have to appreciate just how much of a guessing game this whole thing has been. It's kind of like playing the lottery with millions of dollars. So think of it this way. On one hand, you've got pre-training, where a model just learns the basics of language from the internet. That's kind of like engineering. You have blueprints, you have these formulas called scaling laws, and you can reliably predict what you're going to get. But then there's reinforcement learning. That's where the AI learns its advanced skills, like reasoning. And that part has been like playing the lottery. You just pick your numbers, spend a fortune, and pray you hit the jackpot. And this is where the breakthrough happens. Researchers developed a brand new mathematical framework that basically acts like a GPS for that chaotic world of RL training. For the first time, they have a reliable map to follow. Okay, the heart of this whole map is something called a sigmoidal scaling curve. I know, it's a mouthful, but the idea behind it is actually pretty simple and, well, incredibly powerful. You can take just the first few hours of data from an AI training run, fit that progress to a very specific S-shaped curve, and that curve will tell you exactly where the model is going to end up weeks or even months later. It's literally like seeing the future. And what's so cool about this is that all of that predictive power, it really just boils down to three key numbers. Think of them as the vital signs for any training recipe. First up, you've got A, the ceiling. What's the absolute best this AI can possibly get? Then there's B, the climb rate. How fast is it getting smarter? And finally, C mid, the halfway point. How much raw computer power does it take to get there? By measuring just these three things, you can finally compare different approaches with real scientific precision. So, armed with this incredible new map, the researchers set out to find the ultimate AI training recipe. And this wasn't just some theory on a whiteboard. They launched one of the most comprehensive experiments of its kind ever attempted. And, I mean, they went all in. We're talking a staggering 400,000 GPU hours dedicated to this. They systematically tested every single knob and dial you can imagine in the training process. Different algorithms, different data tricks, you name it. All to find the one perfect combination that would scale the best. And in doing all this, they ran smack into something that AI researchers have suspected for a while, something they call the bitter lesson. And it's a really crucial counterintuitive insight. What works great in a small, short test often fails completely when you try to scale it up to a massive size. And this slide just lays it out perfectly. You've got method A, which looks amazing right out of the gate. It gets good results fast. But then, bam, it hits a wall and just flatlines. It can't get any smarter. Meanwhile, method B starts off slower. It might even look like it's losing at first, but it just keeps on improving and it ultimately reaches a much, much higher level of performance. You see the problem? Without that predictive map, you'd pick the wrong one, method A, every single time. So after sifting through mountains of data, a winning combination of ingredients finally emerged. They call it ScaleRL. And this isn't just a random mix, it's a precisely engineered recipe. It uses something called pipeline RL to make sure the computer chips are always working, which is super efficient. It uses a special math function called CSPO loss to keep the learning process stable, so the model doesn't just go off the rails. It even includes critical details like using high FP32 precision to avoid tiny rounding errors that could ruin the whole thing. Every single piece was chosen for one reason: its proven ability to scale.
Okay, so this is the moment of truth. They had their predictive map, they had their brand new superpowered recipe. Now it was time for the final exam, a massive, high-stakes run to see if it all actually held up in the real world.
This wasn't some small test. They committed a full 100,000 GPU hours to a single, massive run using their new ScaleRL recipe. Right at the beginning, they used their S-curve model to make a bold prediction. This is exactly how well the AI will perform at the very end. And then they hit go and let it run. And the result? It was perfect. Absolutely perfect. After all that time, all that computation, the model's final performance landed exactly where their S-curve, based on just the first few hours of data, said it would. The prediction wasn't just close, it was dead on. The map was real. And you don't have to take my word for it. The researchers themselves put it best, saying that this experiment proved their framework was stable, that it was predictive, and that it was a reliable way to scale up reinforcement learning. Basically, they had cracked the code. Okay, so let's take a step back and talk about why this is such a game changer. Because this isn't just some neat academic paper. This is a fundamental shift in how we build powerful AI. The impact here is it's huge, and it ripples across the entire field. With predictability, companies no longer have to gamble millions of dollars on a training run they're not sure about. With efficiency, we can stop wasting countless hours and energy on experiments that are doomed to fail from the start. And this is a big one: accessibility. Smaller research labs can now run small, cheaper tests and confidently predict how they'll perform at a massive scale. That opens the door for so much more innovation from everywhere. Put it all together, and it's a massive accelerator for the entire field of AI. So at the end of the day, the big takeaway is this: the era of artistry and guesswork in this crucial phase of AI training is coming to an end. It's being replaced by the rigor, the reliability, and the predictability of a real engineering discipline. This breakthrough provides a clear, data-driven path forward for developing more and more capable AI systems. And it leaves us with this really exciting question. Now that we finally have a reliable map for building AI, just how far can we go?